from Caltech.
I got it.
Ryan is an NTN fellow in the Neutrino Theory Network. Just started at Caltech about a month ago.
Yeah.
So he'll be there for a little while. He was previously a postdoc at University of Kentucky, and then did his PhD at McMaster in Canada before that. So Ryan works on all things neutrino, new physics, many interesting experiments. Today he will be talking about the mu to E experiment and how they can use some early data, do some interesting stuff. One thing I'll mention, if you are interested in going for dinner, let me know. We'll leave around 6 or 6:30 after the talk, but take it away.
Thanks. Okay, so thank you for having me. It's great to visit. I've never been to Texas before, so this is a great introduction. So what I'm going to talk about today is this experiment called mu to E, and specifically how to use mu to E to do something it wasn't really designed to do. So you can think of this as a way to get more juice out of an orange. So this is done in collaboration with Richard Hill, Shihua Huang, David Koltik, Pavel Murat, and Yuri Zupan. So Shihua is a PhD student at Purdue. He's on mu to E. He did a lot of work for this. And so a lion's share of all the simulation was done by Shihua, and I just really want to highlight his contributions. All right, this doesn't work. Okay, good. So what is today's talk really going to be about? So it's going to be a simple idea. So just looking for light new physics that's weakly coupled. And so the idea is this thing is rare. It'll be a rare event, but it will be kinematically distinctive. This is kind of like looking through a big pile of hay with your hands. And you'll notice if you get stabbed by a needle. Okay, so you'll know when it happens. So the key is to have a kind of smoking gun signature. And so the simplest thing you can think to do is to focus on two body decays of a particle at rest. And this is a smoking gun signature because that means that this particle, the positron in this example, will be monoenergetic. So you can just look, you know, is there a little bit too much of in one particular energy bin? Do I have too many positrons relative to my standard model expectation? And if I see a signal, I can discover new physics. And if I don't see a signal, I can set limits on perspective model. Okay, so what does that look like in a cartoon form? It looks like something like this, right? So what I've drawn in blue is the Michel spectrum with a bit of smearing that I put in by hand to just mimic detector response. And there would be some peak, right? So there'd be some, if the detector had some finite energy resolution, this delta function will get smeared out over a couple bins. And you see some little bump on top of, you know, as a bump on top of the shoulder of this Michel spectrum. Right. So this seems simple in practice, but you need to get details right. So as I'll discuss later, if this bump happens to lie near this edge, things get more complicated. And maybe as a bit of foreshadowing, in addition to muons, you can do interesting things with pions. Okay, so that's that'll give you kind of a setting experimentally what you might think about. I want to give you a kind of theoretical motivation. So what this talk is really talking about are light new physics particles. And data, just empirical, you know, evidence tells us that any new physics, if it exists, needs to either be heavy or weakly coupled. So if it's heavy, we can't produce it, you know, at conventional or existing colliders. And it doesn't have a large impact on precision experiments because of decoupling. And then there's another possibility, which is that the physics is weakly coupled, but is light. So it can be produced, and it is produced in a host of experiments. And then this just becomes a question of how do you see the signal, right? So this is where digging through a haystack. So mu to E is fundamentally like 100 MeV experiment. That's the kind of energy scale that dictates everything. So there's pions and muons that show up, they decay at rest, and if you're going to get a whack load of these particles, but anything you can look for in this kind of vein of thought is going to be below 100 MeV. So in this kind of, you know, landscape, what kinds of things could we see? And so in this talk, there's three kind of benchmark models we have in mind. So one is an axion or an axion-like particle with lepton flavor violating couplings. So notice here that this axion is coupling to some current that transforms a muon into an electron. Okay, so generically, generically, if we look for muon decays at mu e, we need to think about lepton flavor violation because the signal is going to end up being an electron or a positron, and so you need something that transforms a charged lepton. It transforms charged leptons. So in addition to something like an axion, in fact, in some ways, this Z prime is really just the same phenomenological model as the axion, same basic idea. It's just that you might be theoretically less biased to think that a new Z prime is necessarily very light, right? So an axion, by contrast, is expected to be a Goldstone boson. So if you put me in a room and ask me to guess where on a log plot I would want an axion's mass to lie, I would just always point to the left. Okay, but with the Z prime, I would just throw it there. But from a pheno perspective, these both you can see fall into a very similar classification because they have the same leptonic current sitting here. Okay, and then another class of models, which you might be surprised that you can look for, are heavy neutral leptons. So here I focused on pions as opposed to muons, and I'll explain why later in the talk. This is just basically telling you that you take a standard model current and there's some mixing between sterile and active neutrinos. And so active neutrinos are allowed to talk to the standard model current, but in this case, a volatile pion. Okay, so what I showed you on the last slide, I kind of told you that it's possible there's light in new physics. And I kind of told you, here are some, particles you might look for. And a natural question you might ask is like, where does it end? Maybe this is some slippery slope fallacy. And what I want to stress is, if you haven't thought about this before, that although it's true that if you start postulating light new particles, the possibilities seem to be endless, but in reality, it's a pretty constrained set of options that you have to couple to the standard model. Because if you want your particle to be light and weakly coupled, that means it can't have a charge under one of the standard model gauge groups, or at least an order 1 charge. And that means that the only way I would ever talk to the standard model is through a gauge singlet operator. And there's only so many of these you can write down. So at dimension 4, there's only 4 of them. So there's 2 scalar portals, one that I haven't written here and one that I have. There's a neutrino portal. This naturally, you think about heavy neutral leptons. And then there's a vector portal where you might think about Z primes. So at dimension 5, you kind of have things like an axion like coupling, or you could have a neutrino dipole portal. But even still, once you go through this list, it exhausts itself pretty quickly before, just by dimensional arguments, these higher dimensional operators that you might consider as portals, they become highly suppressed. So there really aren't it's not like there's a wild west of options out here. There's kind of a discrete list of potential ways that any generic dark sector would be able to communicate with the standard model. And so the strategy generically is to look for these portals, right? So any dark sector, if it's going to talk to the standard model, has to do it in one of these kind of countably few ways. And so the idea is to look for these things because they're kind of generic. Okay, so this has kind of shaped a lot of my own interest. So I've written papers thinking about this with like cosmic rays, with solar neutrinos, with cosmic rays again, and with neutrino experiments on Earth, and with atmospheric neutrinos. Okay, and all of these are just examples of taking an experiment that already exists and trying to ask what else it can do beyond its kind of nominal program. And I also want to stress that these are not esoteric or Baroque models. These fit into a broader kind of search paradigm. So this paper, Berryman et al. There's also some other weird authors sitting in the room. This other plot, which is actually from the current work, but is a kind of rehash of some previous work by Urey. They kind of show, that there is a broader experimental program searching for, in this case, heavy neutral leptons, and in this case, axion dark matter. So I just want to point out, like, for instance, in this plot, these colored regions are showing potential constraints that you would get from Dune. the gray regions are existing constraints coming, as you can see, from a number of different experiments. And in what I'll talk about later today, I'll be focusing on this kind of corner parameter space where mu to e can set new limits. Okay, so just to bring it back to what we were talking about, that's the theoretical motivation. So let's pick up where we left off on the experimental side. So the idea here is really simple. It's the simplest thing you'd ever do, which is to just do a bump hunt, right? Okay, so it's rare but kinematically distinctive. And now the question is, how does this work at mu to e, and why is mu to e worth thinking about? So the cartoon picture of mu to e is something like this. So you have a muon beam that comes towards a set of stopping foils. So these are just basically kitchen aluminum foil. And there's a magnetic field that's constantly on. And then there's some helical tracker. So the muons stop in here, an electron or positron comes out. And because there's a magnetic field, the particles move in a helix, right? So whatever their perpendicular component of their momentum is, that's roughly speaking conserved. And so what's shown here is a view down the pipe of this helical tracker. And so what you're seeing, the yellow are these stopping foils, and these rings are different electron or positron trajectories that have left the stopping foils at different, radial positions. So that's why one kisses the tangent of the circle, and another one is clearly intersecting it. And they have different amounts of PT. So depending on the amount of transverse momentum you have, that dictates the radius of your helical trajectory. And so mu to e is basically designed so that most, if not all, of their electrons just pass directly through their tracker, never touching any of their detector components. And this is because their beam intensity is so high that otherwise they would fry all of their components. Okay, and this makes using mu to e to do anything beyond what it was designed to do extremely difficult. So this helical tracker they have, it's been designed to have an extremely good energy resolution. So these are, the region they want to measure are like 100 MeV electrons or positrons, and they're able to get a resolution that's on the order of 150 keV. So it's extremely good. And so this also makes mu to e an extremely attractive experiment for doing a bump hunt, right? Because you benefit from this tight energy resolution. Okay, so what I haven't told you about is what mu to e is actually designed to do. And what it's designed to do is what its logo shows, which is to take negatively charged muons, have them go towards a nucleus. Currently, the design is aluminum, and bind to that nucleus and sit there for a very, very long time. And while they're sitting there, they can do one of two things. They can decay in orbit, or they can capture in the standard model. If they decay in orbit, they almost always will have energies less than 1/2 the muon mass, because if you decay in free space, that's what the spectrum looks like. But occasionally there'll be this long tail extending to higher energies. So if I go back to this plot, decay in orbit, you'd see a little tiny tail that would extend way out here. Okay. Their goal is to see a BSM process where this muon converts, where it basically interacts with the nucleus recoils slightly, and the muon just turns into an electron. And because the nucleus recoils, and it's very heavy, it takes almost no energy, and the signal electron will have almost the entire muon's rest mass as its kinetic energy. So it's basically a 105 MeV electron is what they're looking for.
Just a quick clarification.
Yeah.
So these bindings are happening in the stopping foils?
That's right.
Okay, those are aluminum.
That's right. Yes. But this is kind of a nightmare for doing what I've described as a simple idea, right? There's atomic binding. The muon can actually capture. In fact, half the time it just smashes into the nucleus, and that will emit all kinds of gamma rays. So there's all these backgrounds that are hard to control. And if you want to avoid those backgrounds, you basically have to do what mu to e is doing, which is to look in the high energy tail of the distribution. But unless you're looking for muon conversion, you have a huge loss in your signal rate if you do that. By contrast, if you were doing the experiment with mu plus, You get a clean monoenergetic positron, and the only price you pay is that positron needs to be below the Michel edge.
How narrow of a window are you talking about around that 105 MeV?
They do like a 2 MeV window, but it's kind of an optimization thing because in reality it's not a delta function. There's like a radiative tail, so you can have Bremsstrahlung or various other things, and then so you know in the absence of background, you would just make the window very big so you catch all your signal. But in reality, you then have a decay in orbit background that you're fighting against. So there's some optimization there, and I think they actually have a 1.5 MeV signal window.
But I mean, naively, it's the equivalent of looking for like the endpoint of beta decay, tritium beta decay in cataract, right?
Yes,
There's a huge background if you look.
That's correct.
You want to look at this narrow.
Yeah. Yeah, actually, it's almost exactly like that. And so actually, you can see the design of mu to E. If you are familiar with Ptolemy, the design of mu to E is actually very similar. So you want these really, really thin foils, basically, to minimize how much material. So I think in Ptolemy, they basically have, their design is to have some kind of clever magnetic or electric field gradient. No, I think magnetic field gradient to get the electrons to, when they pop out of the foil, to then like get pulled out along lines so that they never touch anything.
So can I ask one more question about this comparison here?
Yeah.
So the idea is that the mu pluses can still stop in the material, but they're not going to be captured by.
They won't bind.
They won't bind, and so you don't have to deal with.
That's right.
the color.
So mu plus is just, I think anybody who's thought about LS&D or JS&S squared, it's just the same thing that happens in PIDAR. So so the story you hear in PIDAR is exactly what I'm describing with mu plus, just the mu plus just is as a beam that's incident instead of coming from pions in the target. Okay, good. So speaking of pions, I told you that heavy neutral leptons are worth thinking about here. And so I think one thing that's underappreciated about mu to E is that it's actually both a muon and a pion factory. And they try pretty hard to make it not a pion factory, to reduce the number of pions that show up in their experiment, but you can't get rid of all of them. So the way mu to E works is you shoot protons at some target back here, and you kind of like make a bunch of pions in this volume. And then there's also a magnetic field in this region, and it's kind of designed so they get reflected and bounced around, and then they end up in this transport solenoid. And during transit through this transport solenoid, most of the pions decay, but some survive. So the ratio ends up being about 1,000 to 1. And this is nice because that means you're going to get pions stopping in your foils. And if it's pi plus, so if it's pi minus, like in the nominal mu to E run, the pi minus will bind. And then because the strong interaction causes things to happen so quickly, once there's overlap between the pion wave function and the nucleus, you will basically, faster than pions decay in free space, pions will collide with the nucleus and undergo some strong interaction and basically be absorbed. And so that means that for the mu to E run, they can use timing cuts to basically get rid of all the pions, and they have a whole strategy to make sure they never have to think about pions. But for us today, pi plus are going to be a resource, and because they're not going to bind in orbitals, they don't capture extremely quickly. Okay, so what I'm really just trying to tell you is that this is a viable signal channel, and this is a classic thing you would look for in something like pi E nu. Okay, so I've already alluded to this, but the big problem is that mu to E is going to run with a huge sample of mu minus, and you're not going to walk into a room and tell the mu to E collaboration, your idea for your experiment was bad, and you should actually change to mu plus and stop doing all the physics you want to do. Okay, so you have lots of muons, but you have to fight a huge uphill battle if you wanted to use this. So you're kind of, you know, this is basically, I spent a long time trying to think about how to use mu to E to do new physics, and beyond charged lepton flavor violation and muon conversion. And this was always a problem. They basically, the whole experiment is designed to throw out all of the phase space except for the tiny little piece that they cared about. You had all sorts of complications because you had negatively charged muons, and it just looked like it was much harder to repurpose this experiment to do something interesting beyond its original scope than, for instance, a neutrino experiment, which is a huge volume detector, and so anything that has it just allows you to look for anything with a small event rate. Yeah.
What are the arguments for using biases then?
Oh, because you want the whole idea is to look for this muon conversion
On the atom.
Yeah, so the key, right? So let me put it this way. What are your options with charged lepton flavor violation? You could look for mu to E gamma. Or you could look for mu to 3E. Right? But let's say that the okay, and if you had mu to E gamma, you have a non-zero contribution from muon conversion. Okay, so you could ask, why ever bother doing this? Turns out this is competitive with experiments that look for mu to E gamma because of this fact that you can use this special region of phase space, et cetera, et cetera. But specifically, what if this is some heavy mediator, very, very heavy, 10 TeV? Right? Then you obviously can never make it on shell, but this is still totally viable. So it just turns out that this reaction is the best way to see charged lepton flavor violation.
So you're drawing on the fact that the muons like to remain close to the nucleus, the target atom, for a long amount of time.
Yeah, another way you could say it is that so that's right. Another way to say it is that you just have to compete with the muon's free space decay. So both processes, another way to think about it, you compete with the weak interaction. And that means if you think about taking ratios when you compute branching ratios, you're kind of taking your new physics scale divided by MW, which is much more advantageous than the naive scaling that you would expect. There's another little toy calculation that you can do for fun, which is you take a 1s orbital in an atom, and then you think of that as if it were an incident beam on the nucleus, and you calculate the luminosity of a bound atom. And the luminosity is like 10 orders of magnitude or 20 orders of magnitude higher than any experiment that's ever been built. This is an extremely efficient way to get muons to talk to nuclei. You mean the toy calculation I just mentioned? I don't know what the flux of muons is, but they will deliver. It's the same beam that feeds G-2. So, but the lifetime, they will stop 10 to the 18 muons. Yep. So kind of in a POT, if you're used to thinking in terms of POT, that's kind of the, yeah. Okay, so they'll have an unprecedented sample of muon. So the detector has excellent energy resolution. And so all of this looks good until you start looking into the details of the detector. And then it's this funny thing that has a hole in the middle and you just can't do anything with it. Okay, but the good news is that you need to calibrate the detector. And it turns out that if you want to calibrate the detector, you should totally use positive ions. And it turns out that for independent reasons, mu to E was built in this way to be quote unquote charge symmetric, which is that it has a straight barrel in its tracker, and it doesn't care if it's an electron or a positron. They just are helices that move in opposite direction. And that means that it's relatively easy at mu to E to switch to a mu plus B. And it turns out that in our discussions with our experimental colleagues, this was already planned. There were already discussions. So there's a data set that was never expected to be a physics data set. It was expected to just be used for calibrating the detector. But it turns out, as I'll argue, and what follows, this calibration data set, or these two calibration data sets, potentially has like, very legitimately strong physics impact. So this can potentially, it's not just competitive with, but can actually provide leading limits on certain models of new physics. Okay, so this is a more detailed view of what I showed you before. So what's new in the planned mu plus calibration? So I told you that the whole design was basically so that every electron or positron just goes down the pipe. But that's a statement about how strong the B field is. So you can fix that easily by just making the B field weaker, right? Then all the radii that are shown here just scale. And so if you want to target a lower energy scale, it's easy. You just, you know, in a cartoon sense, you just pull a lever and you make the B field weak. Okay. So that's going to put a bunch of Michel electrons into your material, but that also means you're going to have to lower the beam intensity because there was a reason they didn't want these things going through. It would overwhelm their system. And so you kind of have to account for this. Okay. So let's talk about the case I showed you before, which I'll call the easy case. And that's when M is bigger than about 20 MeV. So if M is bigger than 20 MeV, this bump is not close to this edge here. And that means that you will, you can expect that everything will be statistically limited. Everything can be data driven and you don't have to really do, it's kind of a trivial exercise. So just to convince you of this, imagine you're basically doing a bump hunt and you get to measure the data to the right of the bump and the data to the left of the bump. And for a fixed mass, which you specify in advance, by hypothesis, there is no new physics contribution in your left sideband and no new physics contribution in your right sideband. You can make those sidebands as big as you want, you know, or much bigger. A better way to say it, you can make it much bigger than the size of the signal window, and you can therefore get a data-driven estimate for the number of events in the signal window. And then you can just look for an excess and you're totally statistically limited. Any complications of the experiment, you know, you have some weird acceptance that depends on energy, et cetera, that's a smooth function and you can totally account for that. Okay. So one subtlety that we have not solved, but we did spend a long time thinking about, and I think has been kind of neglected in other studies, is that if this particle is lighter than about 20 MeV, this bump moves to within a couple energy resolutions of this edge. So by the way, this blue curve is the same thing as this blue curve. And what I mean by that is it's the Michel spectrum plus the orange bump. But in this plot, you just cannot see a bump on the blue curve at all, because it's extremely hard for our eyes to distinguish this bump on this edge. It basically looks like it just shifts the edge a little. Okay, so it's likely that this search will be systematics limited, and we, you know, tried to solve this problem, but from what I've been told, this is probably a couple of years long endeavor to figure out how to handle this case. Yeah.
Is it possible that if you're in this light regime, though, that this is making your signal, modifying your expectation close to the maximum energy, that this is then a signal you look for in the real data set?
So this is not the maximum energy.
Oh, yeah, that's way out.
Yeah, that's 2 times as high.
Okay.
This is right near the Michel edge. Yeah, so this is hard. Nevertheless, we still, you know, our preliminary estimate suggests that, okay, there's 2 things I'll say. So I'll say those things in one more slide. Okay, so these are our results for 2 different choices of the amount of intensity that you run at, which are fractions of the nominal intensity. I mentioned it needs to be lower. So the blue curve is what we think is realistic if the experiment puts in effort, and the red curve is what's realistic if they put in no effort, related to the data acquisition system. Okay, so there's some question about, you know, kind of pushing the data acquisition system, not really to its total limits, but operating at a kind of high data taking level where you might expect some high level. So that's this blue curve. And that's 1/100th of the nominal intensity, whereas the red curve is 1/1000th of the nominal intensity. So I'll show a chart at the end of the talk, but this improves on leading limits for mu goes to EX by a factor of 40. There's a big improvement. And a good example of an interesting model that this puts constraints on is like a lepton flavor violating Z prime. So this pops out in models of neutrinophilic dark matter, for instance, where you generate these lepton flavor violating couplings by loops that involve neutrinos. Okay, and you have a, I should mention, you additionally have some right-handed neutrino that runs in that loop and gives you a large lepton flavor violating coupling. Okay, if we just ignore this systematic issue and just ask what's the best that mu to E could do, we find a constraint that is very comparable to previous estimates for a future run at mu 3E, for instance, or for MEG2 forward, which is a mu to E gamma, modified mu to E gamma experiment. So all of these other projections for these other muon experiments have the same difficulty. When the axion gets light, you overlap with some standard model kinematic feature, and it's hard to pick out the signal. And this is shown on a plot where you imagine that the axion you're looking for is some axion-like dark matter with that just so happens to have lepton flavor violating couplings. So what you see here is a GA gamma gamma, and mu to E doesn't care about the value of GA gamma gamma, but all of these dark matter search experiments do. These are kind of benchmark dark matter lines. And what you're seeing here is that searches for lepton flavor violation kind of march through this plot to the left. Everything this way is excluded, whereas these kind of direct detection experiments march down. And so these are complementary ways to try and probe this parameter space. This, of course, comes with the caveat that if high scale physics is lepton flavor violating, this is a great strategy. And if it's not lepton flavor violating, then this is focus.
William,
Yeah.
for the previous page, the huge limit, how huge means running for 5 years? Could you give me any kind of the terms?
Here, this one here.
Future, yeah.
Oh yeah, you can't see this on the screen. Yeah, this is actually for 14 days. Yeah, yeah. So this is calibration data. So you will. Okay, so I will say some words about this at the end of the talk. But this is in a matter of days you can set world leading limits. Is the conclusion of all this. So, and this is the first data they would ever take. So there's a number of reasons that are related to the human element of science that this is extremely attractive. Does that answer your question?
Yes.
Okay, good. Yeah, so everything I'll show you is for 14 days of data, and there are various assumptions like nominal beam intensity, or as I'll mention here, a momentum degrader. And we try and make those caveats as transparent as possible. Okay, so what about pi plus? I told you pi plus is cool and is something you can use here. So it turns out the experiment also wants to do an independent collaboration with pion decays, because the standard model has a nice two-body pion decay itself, and that means you get a monoenergetic positron. So you can use that as a calibration feature, but things are more difficult for pions for reasons I'll try and get into, or I will get into. And so this is a plan. It's not guaranteed that it will work, but what's nice is that all of the difficulties that the calibration faces, if you overcome them, you help the new physics search. So these are totally synergistic, and it's totally reasonable. This, if anything, just gives more motivation to actually dig deep and work hard on this, because you'll get a good calibration for your main physics run, and you'll get new physics results. Okay, so what I want to show you is that this red curve is the standard model pi plus to E plus spectrum. And what you see here is a blue curve, right, which is not so much smaller than the red curve. And this is coming from mu plus decay in flight. So this is really simple. Not all of the muons stop. Some of them go right through the foils. And in fact, in the normal mu to E setup, half of them go right through the foils, the higher energy ones. And some of those decay to an electron and two neutrinos. Those electrons can have high energies because just by Lorentz boost, they can go above the Michel edge. And so this is a big thing that we have to fight. And this is what we spent a lot of time trying to understand. Okay, there's some other difficulties with pi plus. So there's this thing called beam flash. So when you turn on the beam, lots of protons, neutrons, photons just smash into vacuum chamber components and other hardware that's surrounding the experiment, and you see that in your detector. It's really prompt. It kind of all happens instantly. But pions only live about a nanosecond. So the pions are also quite prompt. They just so happen to arrive at the detector a little later. So the pions are shown in blue, and I want to draw your eye to the fact that this beam flash curve has been multiplied by a factor of 5, whereas this pion curve has been multiplied by a factor of 1,000,000. Okay, so this beam flash background is a big problem. So what that means is you need to use a pretty tight timing cut. And I think what we end up doing is going from 200 to 300. So you have to throw out almost all the pions. You get to live with maybe some 5%. That's still good enough to do interesting physics. Okay, so you can see this here. Here are, as a function of the momentum of the electron and the time of arrival, here is a plot of potential backgrounds. So Shiva has set up this little black box. This is what we choose as our cut for the signal window. So you pick time between 200 and 300 seconds or nanoseconds, and you look between some 55, slightly above the Michel edge, and 69 MeV. Okay, and what you see is that Michel electrons don't really matter. Beam flash don't really matter. Because of our timing cut. And what really kills us are these mu plus decay in flight. And because they're what really matters, we've increased the statistics by a factor of 25 to better understand this background. Okay, so this is also a big problem if you want to do the pi plus calibration. And so the experiment is going to put in this momentum degrader. So what is a momentum degrader? It's just a big hunk of metal, and it does what it sounds like it does. It slows stuff down. Okay, so this is good for us for 2 reasons. So there's more pion stops, and it slows down the mu plus. So the pion stops is easy to describe. You just estimate how many more stop. It's like 2.5 times more pion stop. But the mu plus, it's a little harder, and you need to actually simulate it because the distribution is just slowed down. So this is uncertain. There's no. This is still under consideration. What the actual momentum degrader design will be. And so what we did is we just introduced this figure of merit. So we estimated from preliminary simulations that this figure of merit will turn out to be 7. And what this figure of merit does is it says we're going to be statistically dominated in a region where the thing is heavier than 20 MeV. And so we'll take the ratio of how many extra pions stop divided by our gain in the background suppression, right? So if there's fewer muons that decay in flight in our signal window, that helps us, but it only helps us like a square root because this is just statistical fluctuation error. So we just take the ratio of this guy divided with a momentum degrader divided by this guy with no momentum degrader. And this gives us our fractional improvement due to the momentum degrader, FMD.
Is this something they want for both the calibration run and for the science run?
No, just for the calibration.
Okay.
Yeah. Let me think about that for a second.
Because it helps you increase your gain flight background. I imagine that might also help for the
Oh.
science run too.
Yeah, but if too many muons stop in this guy, you never want in these experiments that your muon stops in the middle of metal, because then the electron has to pass through some metal.
It will lose energy.
And it will lose, say, an MeV of energy, and then it won't be signal. So you kind of you have to play this game. There was an interesting conversation I had with David Hitlin where he told me that he suspects there will be big improvements for mu to E2 because apparently the beam design for mu to E was totally not optimized for mu to E. It's some old Brookhaven beam design that they just it was convenient to ship over. So there are the reason why I paused is there are questions I think that are currently unanswered about what is the optimal beam design
For E2.
Yeah, but you certainly cannot stick a thick chunk of metal.
Yeah, okay.
Yeah. Okay. So what are the results for heavy neutral leptons? So I've removed any perspective curves for future experiments, and I'm just focusing on what's been done already. So plotted down here is a seesaw target, which is like simple to define. This is just basically where you would get the right neutrino masses in a type 1 seesaw model. Up here, these constraints both come from the TRIUMPH experiment pi e nu. This is a bump hunt. Okay, and it turns out at pi e nu, the bump hunt was good for looking for heavier HNLs. And that meant that they could kind of like look for bumps around the energy of 20 MeV for the positron. This black curve is smooth because this is actually coming from a measurement of the pion goes to positron branching ratio, which is modified by the existence of an HNL, just because there's other decay modes that are available. This blue curve is smooth just because we plotted it. Okay, but in reality, we just assume that there's no luck in the data. But in reality, you would get some shape that would look like this, right? So you're doing a bump hunt here too. So really the curve would end up looking like this, but it would be down here. So imagine putting some jagged shape on top of this. And so you can basically improve by a little less than an order of magnitude on existing constraints from pi e nu. And recently, I was informed by Tim Goringer that there is an experiment called Pioneer at PSI. And this is actually pretty competitive with constraints that Pioneer estimates. Yeah. Yeah. So this is competitive with an experiment that's optimized for doing pion physics, and it's just mu to e's calibration. So I think this should give some illustration that these things are really worth thinking about. This is like this is 14 days with a momentum degrader that improves performance by a factor of 7. And we ran, I think, 1/5 nominal. So another thing is, yeah, I should have mentioned, we kind of, we thought about it for a while and we asked, what should you run the B field at? Yeah, okay, there's not a good picture, so I'll just stay here. What should you run the B field at? And we set it to 76% of nominal. And that basically makes it so that all the Michel electrons go through the pipe. So there's a maximum amount of PT you can get from a Michel electron. And then that lets you run at a high beam intensity. So you can kind of benefit from that.
What does this look like without that momentum degrader?
Marginal with pi e nu.
Okay.
Yeah. A little better in some spots, but not a huge improvement. Yeah.
You're expecting both these cases to be statistics limited.
So this is statistics limited because the plot cuts off at 20 MeV.
So
as you make it lighter and lighter, you will.
If you run longer, you get considerable improvement.
Oh yeah,
Like
yeah.
it's 2 weeks.
Yeah, that's correct. Yeah, you could do this for a longer run if you really care about this, and it may well be this is the best way with near-term experimental programs that you'll be able to probe HNL coupling to electrons.
Well, like now things are changing. So because the stockpile experiments, they're becoming sensitive to 1 MeV to 100 MeV density. And they can probe this region because that's why I was asking for was the pion flux. And for them, they have much higher pion flux and they are not losing anything because of the leak. And so they would get so nobody has done that analysis yet, but just it's like late development.
Yeah, but you're talking about PIDAR experiments, right?
Like a coherent or CCA.
Yeah, but then you're in a huge chunk of material. You can't do these searches. You can't do these bump hunts.
Bump hunts means all you do is produce pi2.
Yeah, but you need to produce it in vacuum. You can't have material surrounding this thing. You need to produce it basically where
you produce it at the target, and then the end comes.
Right, but the reason why coherent or JSNS squared have these huge pion yields, right, is because they just dump a beam into like this thick hunk of metal. There's no instrumentation within that stopping target. You would need something with instrumentation inside the stopping target and to have the pion yields be that high.
Yeah, so just they're stopped pions. So all pions are stopped. 10^23 protons per.
Yeah, but they're not stopped near an instrumented detector.
But are you thinking best of subsequent? You make the HNL and then it decays elsewhere. Yeah. But then
That's very different.
It's a new to N conversion, so you can produce it
I don't think you're producing any of these with the neutrino upscattering.
You can do upscattering, you can produce it from directly from the final decays, and then 20 meters. That's it. That's the detail. And to that way, nobody has done it for stock plan because everybody thought that stock plan can do only the KEP. But now they have opened up with almost zero. So, so 1 MeV to 100 MeV, they don't have much of that. And now that is
Let's sketch this out.
Yeah, sure, yeah. So, so this basically brings me to conclusions. It's a good time to have this talk. So basically the idea is really simple. There's calibration data. It's a valuable resource. You can probe new parameter space for the models outlined in a matter of days. And all this assumes is basically a parasitic run on top of mu plus calibration and pi plus calibration. So we haven't done any optimization on top of that. So it's a whole other discussion that one could have. But that involves convincing the experiment to dedicate resources they may otherwise not dedicate. I just want to remind you, the basic idea, you're looking for light new physics. It's kinematically distinctive. There's well-motivated models that people look for in other contexts. Mu is contributing to this broader effort. And I just want to point out, to give you some idea of what the improvements look like on the muon side, existing limits that are the best for muon to EX are at the 10 to the negative 6 level. We think we can get an order of magnitude or an order of magnitude and a half better using this. That's not surprising because it's muons, right? This is really the wheelhouse of something like mu to E. Potentially, there are other charged lepton player violating facilities that are competitive with just this calibration data set. So that's like mu to E gamma 2. Okay, and then for pions, you can see it on the plot here, but the level of improvement is kind of a little bit better than, a little bit less than an order of magnitude. So by the way, you can see here, like mu to EX1 is like some more pessimistic projections, and you see you're competitive with, but falling short of pi nu by a factor of 2. So that gives you some idea. This definitely depends on some details and how they shake out. But again, 14 days of data at 1/5 nominal beam, and you could run it. I think you can run it at a higher beam intensity if you just work on the data acquisition system. And yeah, so reminder in some context of these axion models, I guess maybe a good figure of merit of why it would really be worth pushing the systematic floor for these massless searches. You actually beat white dwarf cooling bounds. So this is really like you're really pushing really far if you do have lepton player violation model. So with that said, those are my conclusions, and I'm happy to take any questions about stop pion sources.
Yeah, I had it. So, the 14 days of running time, is there a duty factor associated with that? Or? And also
It's
really
kind of like built in, I guess. Yeah. So the way we phrase it is like our constraints are how many muons you would get in 14 days of running.
So is there like a maximum exposure that you can envisage with this?
That all depends on. Okay, so let me just comment a little on why this is nice from the experimental side. This would give you physics results like years before you would actually get the physics results from the main run.
Yeah.
And that would be something that many people would want their PhD students to be able to work on so that they can graduate. But it would also potentially, it would substantially increase the physics output of mu to E. And it would simultaneously, you can imagine all of that implies that you get return on investment for doing a good job on the calibration. So that also just helps things in general. Those are all great when the thing's parasitic. And if you want to start asking questions about maximum exposure, you get into a whole other bag of politics, which is potentially you are no longer symbiotic to the needs and goals of mu to E's nominal run because you're taking away resources. You just take away beam time.
Okay. I mean, I was also curious, what's the exposure for the nominal run?
Much longer, so like, and much higher intensity, so 10, so the 10 to the 13, 10 to the 5 times higher. So 10 to the 18 muon stops instead of 10 to the 13.
And that's
or
with
10
the
to the
higher
12.
intensity and the higher B field.
Yeah.
policies.
Yeah, because then you can just shoot it right through.
And then I have another question. Is it also, so for your new physics benchmarks, you looked at, they're all 2-body decays, right? So you've been.
Yeah, that's right. Yeah.
Is it possible to look at some new physics 3-body decay?
Yeah, we looked at 3-body decays, but then you don't have a bump.
Yeah.
So then you're totally systematics. Okay, so you are gonna have, because of this weird geometry, you don't have a 4-pi detector. So your acceptance as a function of energy has some unknown shape that maybe looks like that. They don't know what that is. They can run Monte Carlo simulations, and you can ask yourself if you believe in Monte Carlo simulation, and you don't. So you need to look in the data, and this is what the calibration stuff is trying to figure out.
Yeah.
So if you do a 3-body thing, you know, maybe you see like, well, what's a 3-body search going to look like? You're going to have the Michel spectrum, you know, and then maybe you have some other subdominant component that maybe has a shape, I don't know, that looks like that, right? So you'd be looking for something that rises like that. But what if your acceptance just has some weird shape there?
Could you not look at where the tail ends? Like there's some.
You mean here?
Yeah.
That's where it's like hardest to look.
That's okay. That's where you were.
Yeah, so you use this as a calibration feature if there's no new physics, but if there is new physics. So yeah, a natural question you might ask is you want to look at like, you want to do HNLs. There's also muon decay to HNL, but that's 3-body. And then, yeah, so I tried to get this to work. It doesn't work.
You bring up the tables that you're trying to see in here?
Yeah.
For the muon one, the top table, what the 90% confidence level limit, what is that a limit on?
Oh, branching ratio. Yeah, I've got it. Yeah, they're
Branching
capped
ratio
in.
mu to EX.
Yeah, that's right. These are all branching ratio limits. Yeah. Yeah, actually at Rice yesterday this came up. So I should say it. So these look impressive, but they pale in comparison to the limit that you is supposed to set, which are, I think, like a single event sensitivity of mu to E is like 10 to the negative 17.
Yeah.
So if one, yeah, so it's kind of insane.
What's the current limit on that? It's like 15 maybe?
10 to the minus 13.
13 or
Yeah. So some huge. Anyways, so I think the moral of this story and why I really wanted to do this project in the first place is that mu to E has so many muons, they better be able to do something. And I hope this motivates other people to think about what you can do with this experiment, because should be able to do something beyond its stated goal.
Awesome. Anyone else?
From this experiment? That's an interesting question. I think there's some interesting interplay and for certain, like there's some model dependence, the ratio of the muon conversion compared to mu E gamma. And I would have to pull up the plot, but I do think mu to E can beat mu to E gamma in certain regions of that.
I was wondering because
Let me.
Well, it's effectively the light axions that you're talking, right? Where you're in systematic regime.
For mu to E
gamma is basically muon to electron in a massless.
Yeah, that's true.
particle.
That's true. Yeah, but there's no, you're not fighting with, actually, wait, let me think. Oh, yeah, you're right. You're right. Yeah, that is a thing. Yeah, mu to E gamma is always asking for better theory for the endpoint of the muon 3-body decay. That's right. That's a,
During the systematics limited region.
yeah. Let me see if I can pull up Bernstein charge lepton flavor violation, and maybe there's a plot in here. Okay, so this is what I had in mind.
We only see the
Yeah, I think I can do that.
classic.
But then, yeah, so what happens here Yeah, there you go. This is exactly it. So there's a kappa, whatever the hell that means. And,
No respect.
when it's tiny, this is better, and when it's big, this is better. I forget what that means.
It's a scaling between different types of lepton member violating.
Yeah, it's two different, higher dimensional operators, yeah. But I forget what they are, so I don't know what small and big means. But the point is, there's, it depends on details, which one's better.
What's the top dash line? Is that the future predictions for UV? And then I see team, yeah. Okay.
That's, I guess, mu to E2's projection. So I said 10 to the negative 17, but that's for single event sensitivity. That's different than their like 95% confidence level. So I think this is supposed to be where.
They could beat U to E gamma constraints on the order of -14, no matter what gamma is.
Yeah, and by the way, I think these are what existed circa 2013.
Uh-huh.
So this is syndrome, I think. So you can see in 2013, there really was this crossover. Yeah.
Awesome. Well, let's thank Ryan again. And like I said, if anyone would like to join for dinner, let me know.